problem. And we're going to go ahead and put some numbers to this. We're going to say that the blue box is 10 kilograms and the green box is 6 kilograms. And for the time being, to make this somewhat more straightforward, we're going to say that there's no friction. That way we don't have to worry about friction. Somebody applies a force of 25 newtons to the box on the left. Can you draw a free body diagram for each box? The force concept model says for each object that you're dealing with, they all deserve a dot, and your job is to draw the force that acts on each of those objects. Just do your best and try and draw a set of arrows here. Back to the stupid physics problem. It is a stupid physics problem. Look, you just draw some arrows, right? None of these are hard. You know what all the arrows are, but I bet there's some mistakes out there, silly mistakes. Did you draw one this way that says 25 on it? I mean, that makes reasonable sense. The 25 is pushing on that box. That box is experiencing a 25 Newton force. Did you draw it over here? Because that box isn't experiencing a 25 Newton force. Right? The 25 Newton is touching the blue box, not the green box. So when you wrote that one on the other side, you did it wrong. And I know somebody did it. Erase it now, no one will notice. Especially if you have like your little pad, you can just no one will see that you're erasing it. The rest of you with real erasers, don't shy away. Make mistakes, it's okay. Did you draw a downwards arrow on this box? Well, it should be like 4 times that size, right? If the 25 was that size, then the 100 has to be 4 times it. When we start trying to think about the size of these arrows, we may need to have more space or be better about thinking about it, which is why I always said start with weight and then go from there, but I broke my own rule. It's on the table, so there's got to be another one up there, right? It has to be equal to that one. And here's the defining moment. It's touching the green box, right? There has to be a normal force this way. And notice, I made the normal force smaller than the 25 on purpose because I think this whole thing is going to go this way. And the only way it accelerates that way is if the forces are unbalanced. None of these rules are new, right? All these rules are the same. I'm applying them the same way every time. So when you guys ask me at tutoring, I don't know, how'd you do that? I applied the rules the same way every time so I can be consistent. So the set of rules are more important. Right? They supersede what we talked about in class. We just apply the rules. And whatever the result is, that has to be what happens in nature. I'm going to draw some more arrows over here. I got to draw one at 60. Well, I think 60 is about that big. And I think there's got to be a normal force. It's got to be the same size. But now, I need a normal force, and it has to be that size. Newton's third law states that the 2 reactive forces are of equal size, but opposite direction. I'm applying the law as stated. So a lot of the mistakes we make is because we miss steps or we apply the laws incorrectly. Any of these laws that we've applied here outside the set of rules we've talked about except for this normal one, which we just learned about today. Now, I know that there are, truthfully, like 3 different normal forces, right? There's this normal force here, there's this normal force there, and then there's those 2 that are sideways. Do the up and down ones matter today? If there's not going to be friction, am I going to use those up and down ones? No, I'm not. So, I mean, they're there, they're important perhaps, but they're not going to influence what happens in this problem because there's no friction. And we know that friction is what's related to the normal force. So generally, we've used normal forces for other things too, but I see balance up and down. I don't think the boxes are going to go up and down. So I'm not going to worry about up and down. I am going to worry about left and right. I'm going to worry about that. Now, there's not a lot to do here, but you'll notice even when I'm doing notes, I don't skimp on writing stuff down, right? I don't skip any steps. I write every step down. Partial credit is disseminated that way. Write more. Don't skip your steps. You'll find you'll get more points that way. If I think the system accelerates, I write net force equals ma. Just write it right in there. And then that reminds me, okay, what's happening in the x direction? I look only in the x direction. And some of you talked about, I got this mixed up. Okay, well, let's not mix it up. Let's be clear. This way, positive. Big and bold. I want no mistake. So anything that points to the right is positive. 25 is positive, but that normal is not. It's pointing to the left. There's a reason why you make a negative sign. Be deliberate. And that equals 10a. I'm going to do the same thing on the other box. But the other box only has this little guy right here. Just him. So n equals 6a. Now, this is a moment where we have to discuss something that maybe you haven't thought of. We know these have to be the same because of Newton's third law. Have to be. For every force, there's an equal and opposite reactive force. They are the same size. Do these have to be the same? Do the two boxes accelerate at the same rate? It's an important question to ask. If the blue box accelerates more than the green box, that means the blue box is being crushed, right? If this one accelerates to the right faster than this one, it's moving, the blue one's moving into the green one. Does that make sense? And if the green one accelerates faster than the blue one, then they're no longer touching. I think it's not unreasonable to say that they probably have the same acceleration. The two boxes move together. It's a reasonable question to ask, and one you should ask. Are the two boxes in some way joined together in their motion? I think it makes sense that the two boxes are moving at the same acceleration. Otherwise, like I said, one's being crushed or they're separating. And I'm not saying that boxes don't get crushed. They do all the time. Look at every Amazon shipping thing. It's always coming to my house all crushed. But apart from that, I have 25 minus n equals 10a, and n equals 6a. Every single one of these problems is going to have a force that is equal and opposite, that's inside the system. In fact, this normal force is called an internal force. It's internal to the system of boxes. The 25 Newton is an external force. It is external to the system of boxes. Something from the outside is applying that force. Some guy is pushing on the boxes. He is external to the system. But in the box system, the normal force occurs between the two boxes. It is internal to the system. So we will start talking about the difference between external forces and internal forces. But ultimately, there's some pretty simple math to do here, right? I see the math laid out in front of me. Do you see it laid out in front of you? I can get rid of that normal force. We're always going to get rid of this Newton's third law of force because it's equal and opposite. The equations will always have one negative and one positive. Just add them together. 25 equals 16a. Well, I didn't know what the question was, but I'll remind you. At the end of doing the force concept model, you can either find an individual force or you can find the acceleration. It appears as though that doesn't change. Even now, I could find the acceleration of the system. Do you guys see that okay? Now, the acceleration is 25 divided by 16. I don't know what that is.
1.56.
Oh, no. 1.56. Now, there's more to these kinds of questions. Like I could say, well, now that we know that, could we figure out the force on the boxes? Sure, you could. You could go back and figure out the force on the boxes. You could even ask yourself, is this force big enough to crush the boxes? When we look at what's actually happening to the boxes, this box is experiencing forces on either side that are trying to crush the box, right? That normal force is pushing on this box right there. And I'm trying to push the boxes, so I am crushing the box. That normal force is big enough, I probably would crush the boxes. Do me a favor, find out what the size of that normal force is, please. Just take a minute. It's whatever 6 times 1.56 is. I don't know what that is. It's like 9 or 10. What is it? 9.4 newtons. Okay, I'm going to ask you an important question, and I don't know that you can jump to the answer. If, it's the big if I took those two boxes and I switched them, so the green box was first and the blue box was second. So green box, blue box, and I instead pushed on the green box. What do you think would change about this situation? Do you think the acceleration would be the same, or do you think it would be different? Here's what I want you to try it. I didn't change hardly anything, right? I'm just pushing on the other side. Can you just tell me two things? Tell me the acceleration and the normal force. And we're on special schedule today, so you have 2 minutes. If you're doing the work, I applaud you. Did you do that? Seems reasonable, right? I'm not drawing the up and down ones, don't need them. Did you do that? All seem good? I'm just doing the same things as before. But I am going to do this. I'm going to take that sucker over there, and I'm going to add them together and find this part came out exactly the same as before. Would you agree with that? You get that too? So A is going to be 1.56 meters per second squared, just like before. However, normal equals 10 times that 1.56. Do you see that the normal force changed when we changed where we applied the force? It got bigger. We pushed on the small box, and the normal force got bigger. Hear me out. Which of the two boxes boxes needs more force to accelerate? The big box or the little box? So this force gets distributed. More of it went to the big box than the little box because they both accelerate the same. All right.